A coding theory of time-of-flight imaging. Time-of-flight imaging systems are used in various depth sensing applications. Continuous wave time-of-flight cameras are particularly attractive due to their low power and low cost requirements. Some of these 3D applications require high depth precision for a wide range of depths. However, current 3D cameras do not have the depth precision or range required for these applications. Our goal is to increase the depth resolution of time-of-flight cameras without decreasing their depth range. Continuous wave time-of-flight cameras work by periodically modulating the intensity of a light source according to the source modulation function. The radiance incident on the sensor will be a shifted and scaled modulation signal. This signal is then correlated with the sensor demodulation function. The resulting intensity measurement will be a function of ambient illumination, effective albedo, and the phase difference between modulation and demodulation signals. Therefore, 3 or more intensity measurements are required to solve for these 3 unknowns. Most current time-of-flight cameras use sinusoid coding, where both modulation and demodulation signals are phase-shifted sinusoids. The correlation functions are also sinusoids. We have developed a geometric framework for analyzing the performance of time-of-flight coding schemes. For a valid coding scheme, the correlation functions will parameterize a closed curve in the k-dimensional intensity space. We call this the coding curve. Using the abstract view of the coding curve, we can show that in the presence of noise, traditional sinusoid coding achieves low depth resolution. We find that the depth resolution of a time-of-flight camera can be increased by using codes with long, locality-preserving, non-self-intersecting coding curves. One family of curves that satisfy all of these properties is Hamiltonian cycles on hypercubes. Due to the length and locality-preserving properties of this curve, adding noise leads to small depth errors. Based on this coding curve, we can generate the correlation functions that parameterize it. These are the corresponding Hamiltonian correlation functions for the case of 4 and 5 measurements. We demonstrate the performance of Hamiltonian codes in a typical 3D scanning scenario. Hamiltonian codes achieve an order of magnitude lower depth errors. This allows them to recover fine 3D structures of the scanned face. Hamiltonian coding can be implemented using a high-power pulse laser and an arbitrary function generator. This implementation is not compatible with the practical constraints of consumer continuous wave time-of-flight cameras. Consumer time-of-flight cameras require the modulation function to have finite peak power. Furthermore, the modulation and demodulation signals should be binary. This constraint follows from the fact that most time-of-flight cameras rely on digitally generated square wave signals. Finally, the output modulation and demodulation functions should adhere to the system's band limits. While the input functions given to the system are required to be binary, the output functions, after passing through the system, have a limited bandwidth. The output functions produce the final correlation. Fortunately, given hardware constraints, we can factorize Hamiltonian codes into practical modulation and demodulation functions. Due to the finite bandwidth, the constraint functions only approximate the Hamiltonian correlation functions. Nonetheless, the new practical Hamiltonian codes continue to achieve higher depth estimation accuracy under a wide range of SNR levels, despite imposing strong hardware constraints. The next step in this line of work is to evaluate our proposed codes in a commercial time-of-flight camera. In summary, we have developed a geometric framework for analyzing and designing time-of-flight coding schemes. This framework enabled the design of Hamiltonian codes which achieve higher depth precision than conventional codes. Furthermore, we demonstrated that Hamiltonian codes can be realized even under strong hardware constraints. When implemented in a commercial time-of-flight camera, this new family of coding functions will increase their depth resolution without affecting power consumption, total exposure time, processing time, and spatial resolution. Thank you.